Hello everyone and welcome to this new video. Today we're talking about wave optics. Now just in the previous chapter you learned a lot about ray optics, and both of these are nothing but the study of light. So the first question of course is, when do we talk about ray optics and when do we talk about wave optics? And the answer to this lies in the analysis of the nature of light itself. You see, the wavelength of light is so small that when we are dealing with objects like prisms and lenses and mirrors, all these objects which we were dealing with in the chapter ray optics, when we deal with such objects, the wavelength of light is very small as compared to these objects. And in such a case, it is safe to assume that light is a straight line. So what we do is we assume that light travels in straight lines, and we do so in the field of ray optics. And we're only allowed to do that because we are dealing with macroscopic phenomena. That is, we are dealing with objects whose sizes are much bigger than the wavelength of light itself. So that was the field of ray optics, where the main idea was to treat light as a straight line. But on the other hand, what is wave optics? Well, when you look at objects whose sizes are similar to the wavelength of light, in such a case, we will not be able to use ray optics. We will have to use a different kind of field of optics, and that is wave optics. So we say that when the size of the object is comparable to the wavelength of light, then at such a case, we can no longer ignore the fact that light has a wave-like nature, and in such cases, we have to use wave optics. So we say that wave optics is used when the size of the objects we're dealing with is almost similar to the size of the wavelength of light itself. In such a case, we deal with wave optics. So this is the branch of physics which deals with the wave nature of light, and hence the name wave optics. So let's first take a look at why wave optics was even required. Well, you see, early on, when scientists were trying to study the nature of light itself, Isaac Newton was of the opinion that light is made up of particles. And he said that these particles were nothing but corpuscles. He called them corpuscles, and he said that these particles have negligible masses. However, there was some problem with this theory. This theory was not able to explain some well-known phenomenon like interference and diffraction and polarization, all of which we'll see very shortly. So because this theory was not able to explain any of these different phenomena, this theory had to be rethought upon. And along came Huygens. And Huygens said that maybe light is not made up of particles, maybe light is made up of waves. So he proposed that the light is made up of waves, and when he did this, he made a wave model of light, that is wave optics. And when this theory came, it was seen that this theory was better than the corpuscular theory of Newton, and this theory came to be known as Huygens wave theory of light. The main principle of this theory is that light is traveling in the form of waves. So basically there was this big debate between Isaac Newton and Christian Huygens, and one of them was right and the other was wrong. Isaac Newton's theory, which was the corpuscular theory of light, said that light, when it went into a denser medium, will have a greater speed as compared to light in a rarer medium. Christian Huygens' wave theory predicted the opposite. It said that when light travels from a rarer to a denser medium, its speed actually reduces. And we know which one of these is the right answer. We know that the speed of light reduces in a denser medium, and thus it was a win for Huygens' wave theory of light. Similarly, Newton's corpuscular theory could explain rectilinear propagation of light, reflection and diffraction, but it could not explain interference, diffraction or polarization. Huygens' theory, on the other hand, could explain all of this and clearly was the winner between the two theories. It is Huygens' wave theory of light that we will be studying in this chapter in the field of wave optics. So what is the wave theory of light? The wave theory of light, which was given by Huygens, that is Huygens' principle, basically says that every point on a wavefront is a source of wavelets which spread out forward at the same speed. Now, of course, the first question to understanding the principle is that what is a wavefront? Well, let's understand what is a wavefront with an example. Let us say that we drop a small stone on a calm surface of water. We notice that waves spread out from the point where the stone has landed. If we take a picture of the surface, we would see circular rings moving out from the point of disturbance. These circular rings indicate maximum disturbance. All points on this ring are oscillating in phase because they are at the same distance from the source. This ring is then known as a wavefront. Thus, a wavefront is nothing but a surface in which all the points oscillate in phase. A wavefront is thus defined as a surface of constant phase. The speed with which the wavefront moves away from the source is known as the speed of the wave itself. The energy of the wave travels in a direction perpendicular to the wavefront. Rays originating from a source of disturbance, which are perpendicular to the wavefronts, are known as wave normals. There are three different types of wavefronts. The first one is the spherical wavefront. A spherical wavefront is emitted from a point source. If you have a point source which is emitting waves uniformly in all directions, then if you join all the points which have the same amplitude and are vibrating with the same phase, then the surface that you create will be a sphere. And this surface is what is known as the spherical wavefront. On the other hand, if you have an extended object which is a linear source of light like a tube light, then the light propagating from this linear source of light will propagate in the form of cylindrical wavefronts. Finally, if the object is situated at a very large distance from the source of light, then even a small portion of the spherical or the cylindrical wavefront will appear to be a plane, and we have then what is known as the plane wave. And thus, for objects situated at very large distances from the source, we assume that the light is reaching the object in the form of plane wavefronts. Huygens' principle gave us a way in which we were able to determine what is the shape of the wavefront at some later time if we knew the shape of the wavefront at some initial time. And we could do this simply by a geometric analysis. And thus Huygens' principle is nothing but a geometrical construction which allows us to predict what will be the shape of the wavefront at some later time if we know the shape at some initial period of time. So let's undertake this geometrical analysis. Basically, if we have a point source of light which is emitting waves in all directions, then Huygens' principle said that this is a spherical wavefront and every wavefront will give out secondary waves in all directions. Thus, we say that every point on this primary wavefront will act as a secondary source of light and send out secondary waves in all possible directions. The radius of this circle will be nothing but the distance travelled by light in that particular period of time. Now, Huygens' principle says that all you have to do is draw a tangent to all these circles, and this new surface that you have created is the new shape of the wavefront at that later time t. And so the resultant wavefront at any position is given by the tangent to all the secondary wavelets at that instant. But there is one catch to this geometrical construction. I can also draw a tangent to the circles on the inner or the backward side. However, the wavefront will never travel in the backward direction, and therefore Huygens said that you must only consider the direction of the secondary wavelets in the forward direction and therefore ignore its movement in the backward direction, and thus only look at the new wavefront that you have created in the forward direction. And now thus what you have obtained is the new position and shape of the wavefront at a later time t. This actually tells us that the secondary wavefront is retaining the form of the primary wavefront, which means that a wavefront always travels parallel to itself. You can see that the new shape is parallel to the old shape of the spherical wavefront. A similar analysis can be undertaken if you have a plane wave emanating from a cylindrical or linear source of light. In such a case, again, we consider only the forward direction, and therefore we obtain the new position of the plane wave after time t. Thus, Huygens' principle through geometrical analysis enables us to find the new shape of the wavefront. So we claim that the wave theory of light was successfully able to explain reflection and refraction. Let's see how Huygens wave theory was able to explain the laws of reflection. The first thing I'd like to explain is that even ray optics was able to successfully explain reflection and refraction, and now we are looking at the same phenomenon, that is reflection and refraction, but from the point of view of wave optics. So there must be some connection between ray optics and wave optics when we are looking at the same phenomenon. In ray optics, we always took light in the form of rays, that is in the form of straight lines. In wave optics, we are going to look at light in the form of wave fronts. So let's see how we are going to look at reflection from the point of view of the wave theory of light. Let's say I have a reflecting surface xy, and incoming light is shown in the form of straight parallel lines. And because I have drawn parallel lines, that is parallel rays of light, we know from ray optics that this means that the source is at a very large distance. However, in wave optics, if the source is at a very large distance, instead of showing parallel straight lines, what I should be showing is a wave front. So how exactly will a wave front look in the same situation? The wave front will be drawn perpendicular to the rays of light. In wave theory, you will actually be doing the opposite. You will first draw the wave front, and perpendicular to the wave front will be the rays of light. So A1P is here a planar wave front that we have drawn, which is representing the light which is coming and going to fall on the reflecting surface xy. Now as you can see, the ray which is beginning from A reaches xy at point A1, and the ray which is beginning at B reaches xy at point B1. And it is very clear that the ray at B has to cover extra distance which is equal to PB1 just to reach xy. So the ray at B is covering an extra distance of PB1 to reach the surface xy. Our goal is to find out what is the explanation for reflection from the wave theory of light. So what we are going to do is use Huygens principle. Huygens said that every point on the wavefront will act like a secondary source of wave. Initially, we will only be considering the waves which are beginning from point A1 and P. The wavelets which begin from point A1 will travel in the upward direction, whereas the wavelets which begin from point P will travel in the downward direction. This is because point A1 already lies on the reflecting surface, and therefore any wave which is starting from A1 has no place to go in the downward direction, but it is reflected from the first instant of time back into the same medium. Thus we say that if t is the time required for the wave to travel from point P to B1, then in the same time period we have to draw the wavefront at point A1 to show what is the distance travelled by the wave at A1. And thus what we do is we take a compass, and this compass has a radius equal to PB1, and we draw the secondary wave at B1. This is the wave as it reaches reflecting surface xy after time t. We are going to take the same radius and draw a secondary wavefront at point A1 as well. Thus we have drawn the position of the wave which is starting from point A1 and point P after the same time t. So when the wave starting from point P reaches B1, the wave starting from point A1 will have reached R. The tangent to these hemispheres is what gives us the new position of the wave front, and thus the new wave front is RB1. And as said before, the rays which are reflected will be found by drawing perpendicular lines to the wave front. A1t and B1q thus represent the reflected rays. The distance covered by the secondary waves to go from A1 to R is the same as the distance covered by the waves to go from P to B1, and since both these lie in the same medium, this distance is equal to Ct in both cases. Thus you can see that in time t, waves move from P to B1 and from A1 to R. Here we considered only the waves starting from point A1 and point P for ease of understanding. However, one can draw the waves which begin at the points in between A1 and P. At every point, the wave starting from the points between A1 and P will reach XY after the wave starting from A1 and before the wave starting from P. Once the wave from P reaches B1, our analysis is complete, and this surface touching all the hemispheres is RB1, which is our reflected wavefront, bounded by the reflected rays A1R and B1Q. Thus, we have found the reflected wavefront from the point of view of the wave theory of light. Let's now see if we can prove the laws of reflection. In triangles A1RB1 and A1PB1, we see that A1B1 is a common side. A1R and PB1 are both equal to CT and both have a 90-degree angle. Thus, these two triangles are congruent, and this proves that all the other elements of the triangle might be the same, and hence we say that angle RB1A1 is equal to angle PA1B1, and because RB1A1 is nothing but R and PA1B1 is nothing but I, we get that I is equal to R, which proves the first law of reflection. We also see that the incident ray, the normal and the reflected ray all lie in the plane of the paper, and thus the second law of reflection is also verified. Thus we show that the wave model successfully explains the laws of reflection. Refraction of light can be explained on the basis of Huygens' wave theory of light in the same way that we were able to prove the laws of reflection. In this case again, we have a surface xy, but in this case the surface is a refracting surface. And as before, we assume that rays are parallel when they fall on this surface. So the incoming incident rays AA1 and BB1 are parallel as they reach the refracting surface xy. And as before, we consider a planar wavefront which is perpendicular to these incident rays, and thus A1P is my incoming wavefront bounded by the rays AA1 and BB1, and it is moving towards the surface xy. Now, as before, it is clear that the ray which is beginning from point B has to travel an excess distance when it tries to reach the surface xy, and this excess distance is nothing but the length PB1, and therefore now again we will draw the secondary waves which are beginning from the wavefront A1P, and as before we will first only consider the waves which are beginning from points A1 and P. However, there is one important difference in the way we will construct the secondary waves in this case and the way we did it for reflection. The waves which will begin from points A1 and P will both be moving in the downward direction. This is because xy is not a reflecting surface but a refracting surface, and therefore the wave will propagate into the medium, which in this case is glass. And thus, when I draw the secondary wave, even at point A1, I will draw the hemisphere in the downward direction. But it is important to notice that because the speed of light is less in glass as compared to air, the radius of the hemisphere which I will draw at A1 will be less as compared to the radius that I will draw at P. Let's say that the time taken for the wave to travel from point P to B1 is T, then I will draw a hemisphere which has the radius PB1, and thus according to Huygens' principle, I am saying that secondary wavelets are originating from A1 and P and are going to spread over a hemisphere in time t, and to draw this hemisphere, I take the radius PB1 and I draw the secondary wave at B1, and because glass is denser than air, the distance travelled by the wave starting from A1 is less than the wave originating from P, and thus now I will reduce the distance in my compass approximately. Since this is a qualitative analysis, I will reduce the distance in my compass and draw a smaller hemisphere inside the medium of glass. So basically what I just want to show you is that the distance travelled by the wave from point P to B1 in time t is greater than the distance travelled by the wave from point A1 in the same time t, because the speed in glass is less than in water. Now, of course, you draw the tangent to both these hemispheres and obtain your refracted wavefront, that is B1r, and this refracted wavefront is your wavefront in glass. Once you have this, you will draw the refracted rays by making perpendiculars to the wavefront, and thus A1r and B1r are the refracted rays. Now, if we assume that C1 is the speed of light in air and C2 is the speed of light in glass, then PB1 is equal to C1t, whereas A1r is equal to C2t. And thus we see that the wave starting from P has covered the distance C1t to reach B1, and the wave starting from A1 has covered the distance C2t to reach the point R. Now, we considered the waves only from points A1 and P for the ease of convenience, but of course, the waves will start from every point on the wavefront, and all the waves between AA1 and BB1 will reach XY and spread over hemispheres of decreasing radii in glass. And the tangent to these hemispheres is nothing but our refracted wavefront B1r obtained in glass. Finally, let's see if we can prove the laws of refraction using this wave theory of light. In triangle A1PB1, we see that sine I is equal to PB1 upon A1B1, that's opposite upon hypotenuse, which is nothing but C1t divided by A1B1. Similarly, in triangle A1RB1, I get sine R, which is A1R upon A1B1, which is nothing but C2t upon A1B1. We now divide equation 1 by 2, and we get that sine I upon sine R is nothing but C1t upon A1B1 upon C2t upon A1B1, and A1B1 cancels and t also cancels, and we get that sine I upon sine R is equal to C1 by C2, which is by definition the refractive index of the second medium with respect to the first, and thus we have proved Snell's law, and thus proved that sine I upon sine R is equal to mu 2 with respect to 1, and we know this is Snell's law, and thus we have proved the laws of refraction using the wave theory of light. The action of prism, lenses and mirrors can be explained on the basis of the wave model. For example, when a wavefront tries to travel through a prism, we can see from the shape of the prism that different parts of the wavefront have to travel different thicknesses of the glass prism. For example, the bottom parts of the wavefront have to travel through the thickest distance of glass, whereas the top parts have to travel the least distance in glass. And because we know that the speed of light in glass is less than the speed of light in air, it is obvious that the bottom wavefronts will be slower than the top wavefronts. However, the time taken by the ray Kp to travel from point K to K dash is the same as the time taken by the ray Lr to go from point L to L dash, because what we are drawing are wavefronts, and all these points will reach the same distance in the same period of time. And therefore, I can say that Kp upon the speed in air plus Pq upon the speed in glass plus Qk dash upon the speed in air is equal to the time taken by the ray Kp. And similarly, Lr upon the speed in air plus Rs upon the speed in glass plus Sl dash upon the speed in air is equal to the time taken by ray Lr. And because both these rays will reach the same points in same periods of time, and because the lower parts of the wavefront have to travel a greater distance in glass, they are slower as compared to the upper parts, and therefore in the same period of time, if we take a look at them, we'll see that the lower part is slower and hence it's a little bit behind, whereas the upper part is faster and hence it is moving forward as compared to the lower part. And thus you can see that the emerging plane wavefront K dash L dash is obviously bending towards the prism. The same analysis can be extended to spherical lenses. A convex lens is thick in the middle and thin at the edges. Thus, when a plane wave front is incident on a convex lens, different portions of this wave front travel through different thicknesses before emerging. Clearly, the distance travelled at the center is maximum and the distance travelled by the wavefront at the edges is minimum. As light travels slower in the lens material than in air, the refracted wavefront is clearly a converging wavefront. Thus, if we draw the rays of light which are normal to the wavefronts, we'll see that on passing through a convex lens, the parallel rays will tend to converge. On the other hand, a concave lens is thick at the edges and thin at the middle. When an incoming wavefront is incident on a concave lens, the wavefronts which are travelling through the edges are slower as compared to the wavefront travelling through the center of the lens. And because the speed in the lens material is slower than the speed of light in air, the wavefront is clearly a diverging one. If we draw the rays of light by drawing perpendicular to the wavefronts, we'll see clearly that parallel rays on reaching a concave lens diverge from it. When the incoming wavefront is incident on a concave mirror, the center of the wavefront travels the largest distance to the center of the mirror before getting reflected. The edges of the wavefront have to travel the smallest distance before getting reflected. Therefore, the reflected wavefront is clearly a converging one. Just like Doppler's effect in sound, Doppler's effect is also exhibited by light waves. The logic remains the same. Whenever there is a relative motion between the source of light and the observer, the frequency of light which the observer measures is different from the actual frequency of light emitted from the source. When the source of light is moving towards the observer, the frequency measured by the observer increases. The frequency measured by the observer is greater than the actual frequency of light. On the other hand, if the source of light is moving away from the observer, then the frequency measured by the observer is less than the actual frequency of light. Thus, we say that the apparent frequency of light increases when the distance between the source of light and observer is decreasing, and the apparent frequency of light decreases if the distance between the source of light and observer is increasing. An important difference between the Doppler's effect in light and sound is that the Doppler's effect in light is simpler in the sense that it doesn't matter whether it's the observer moving away from the source or the source moving away from the observer. Both of them are counted as the same situation. Thus, we can write the formula for the case when the source and observer approach each other. Let's say that the source and observer approach each other with a velocity v along the direction of propagation of light. In this case, the apparent frequency or the frequency measured by the observer mu dash is given by mu 1 plus v by c, where v is the velocity with which the source and observer approach each other. Clearly, the apparent frequency is greater than the real or the actual frequency. Because the observer measures an increased frequency, we can also say that he measures a decreased wavelength of light. And thus an increase in frequency is a decrease in the wavelength, and thus this effect is represented by a blue color, also known as the blue shift. On the other hand, if the source and observer are moving away from each other with a velocity v, then the apparent frequency is obtained by replacing v by minus v in the above formula, and we get that the apparent frequency is equal to the original frequency multiplied by 1 minus v by c, and clearly the apparent frequency is less than the original frequency. And thus, when the observer and source are moving away from each other, the frequency decreases, which means that the wavelength is increasing, and because the red is the greatest wavelength in the visible spectrum, this is also associated with the term red shift. From this, we can combine the two equations and write a general formula which is given by the apparent frequency equal to the original frequency multiplied by 1 plus minus V by C, where plus stands for the case when they are approaching each other and minus for the case when they are moving away from each other. We can also write down the analysis of the shift in the frequency, that is delta nu, which is nothing but apparent frequency minus original frequency, is given by plus minus nu by C into V. This is negative if the source and observer are moving away from each other, that is apparent frequency decreases or apparent wavelength increases, and this is known as the red shift. On the other hand, the shift is positive when they are moving towards each other, the frequency increases or the apparent wavelength decreases, and this is known as the blue shift. After explaining reflection and refraction on the wave model, our next goal is to be able to explain interference, diffraction and polarization based on the wave nature of light. After all, that was one of the principal advantages of using the wave theory as compared to using Newton's corpuscular theory of light. Now, if I want to study what interference is, before that I must understand the superposition principle. Now, you've heard of the superposition principle many times before. Like, for example, you have heard it in wave mechanics. The superposition principle there was applied to waves, but those were mechanical waves. And today we're applying it to light waves, which are electromagnetic waves, but the principle remains the same and is equally applicable to those waves in wave mechanics and these waves in light. So the superposition principle basically deals with the fact when you have more than one wave reaching the same point in a medium. In such a case, we say that these waves are superposing each other, that is, they are coming one on top of the other. And then in such a case, superposition principle says that when two or more waves traveling through a medium superpose each other, that is, reach a point together, then a new wave is formed in which we find the resultant displacement by vectorially adding the individual displacements of the wave which was reaching it. That is, the resultant displacement, let's say y bar, at any instant is equal to the vector sum of the displacements due to individual waves at that instant, and therefore the resultant displacement y bar is equal to y1 bar plus y2 bar plus y3 bar plus y4 bar, and so on and so forth, depending upon how many waves are reaching that point at that instant of time. So here, for example, through this animation, we can see that no matter what happens, the waves behave as if the other one is not present. So each wave contributes irrespective of whether the other is present or not. And what we are doing is actually adding these contributions at every single point. In such a case, we see that when the crest or the maximum position of one wave falls on the maximum position of the other, the amplitudes line up and the amplitude of the resultant wave is nothing but the addition of the two waves. On the other hand, when the crest of one wave falls on the trough of the other, that is on the minimum position of the other, the amplitude of the resultant wave is given by the difference of the amplitudes of the two waves. This is the superposition principle, and we will apply this principle to light waves to understand the phenomena of interference and diffraction. Now, we said that we will need to apply the superposition principle in order to explain interference. But in order to obtain interference in the first place, the sources of light that you need to use must be coherent. And therefore, the concept of coherence and incoherent light sources is extremely important to the understanding of interference. Coherent sources are those that have the same wavelength, same frequency, and they are in the same phase, or they have a constant phase difference. In such a case, the sources are said to be coherent sources. In the simplest of words, two sources will be coherent if the waves exactly match each other. That is, if I can completely overlap them with each other. However, they are also coherent if they have a fixed shift between them. That is, as the waves move in time, this shift does not change. Effectively, this means that two sources are coherent when the waves they emit maintain a constant phase relation. That is, the waves do not shift relative to one another as time passes. So as compared to these two set of waves that you see on the screen, what will incoherent sources look like? Two sources which are randomly shifting with respect to each other in time. That is, if the pattern of one source shifts forward or backward by random amounts at random moments, then on an average, there will be no stable relationship between the two wave patterns and interference will not be observed. Thus, in order to observe interference, what we need are coherent sources. So, how do we get coherent sources? Two independent sources of light can never be coherent. In order to obtain coherent sources, you have to split the same source, and therefore I say that two coherent light sources can be obtained from a single source of light. We have finally concluded that in order to see interference, we'll need to use coherent sources of light. We can also conclude this mathematically. Since we know that light waves are electromagnetic waves, we can apply the superposition principle to two light waves and see if interference is mathematically obtained. Let the oscillating electric field produced by the first source at a point be E1 and that by the second source at the same point be E2. And then E1 is given by A1 cos omega 1 t plus phi 1 and E2 is given by A2 cos omega 2 t plus phi 2. Here A1 and A2 are of course the amplitudes of the wave, omegas are the frequencies and phis are the phases of the waves. Now I know that the intensity of a wave is proportional to its amplitude and therefore the intensity produced by the first wave at the point P will be given by k E1 square, and taking E1 from equation 1 I get that I1 is equal to k A1 square cos square omega 1 t plus phi 1. Similarly, the intensity produced at the same point P by the second wave will be given by k E2 square, and E2 will be replaced by the equation 2, and this gives me I2 is equal to k A2 square cos square omega 2 t plus phi 2. This gives me the two intensities of the wave, and I'm saying they reach the same point P, and therefore I will apply the superposition principle. But keep in mind that the superposition principle is applicable to the electric field and not the intensity directly. And therefore, first I will apply the superposition principle to the electric field, and I say that the total electric field at the point P will be E1 plus E2, and therefore the new intensity of the resultant wave at point P will be k E1 plus E2 the whole square, which will be equal when you open up to k E1 square plus k E2 square plus 2 k E1 E2. This shows that the final or the resultant intensity I, which is nothing but k E1 plus E2 the whole square, is equal to k E1 square, which is the term I1, plus k E2 square, which is the term I2, plus this extra term, which we will call as I12, and this extra term is the interference term. And thus you see, mathematically even, I get this extra part in my intensity, and this extra part is what is telling me that there is going to be interference. And we only get this extra part when the sources that you consider are coherent. And this extra part comes out to be 2 root I1 I2 cos phi 1 minus phi 2. And thus we see that interference can only be obtained effectively when we have coherent sources. And so finally I say that the condition for interference is that we need two sources with the same frequency and with a constant phase difference, and such a pair of sources is coherent sources, and we need coherent sources for interference. And thus when illumination is done by two coherent sources, the resultant intensity is given by I1 plus I2 plus I12, where I12 is nothing but 2 root I1 I2 cos phi 1 minus phi 2, which is the interference term. So what even is the interference of light? Well, if you have a single source of light and you observe how the light is distributed around it, you'll see that the distribution is uniform in all directions. However, if you have two coherent sources of light, you'll see that in the medium surrounding these sources, there will be points at which the intensity will be high and there will be points at which the intensity will be low. And thus you see that the light energy around these two coherent sources will not be equally or uniformly distributed in all directions. And thus we see that there is a redistribution of light energy, and this is known as the interference of light. And therefore by definition, it is the phenomenon of redistribution of light energy in a medium on account of the superposition of light waves from two coherent sources. And thus you can see in the definition itself that here I have the two words that we needed. We have applied the superposition principle and we require that the sources are coherent. And from this we will get interference, which is nothing but the redistribution of light energy. Some places it is brighter and some place it is darker. The places at which we obtain brighter points or points of high intensity are known as maximas, because at these places the two waves are completely lining up with each other, and such an interference condition is known as constructive. On the other hand, at the points where the intensity is low, that is at the dark points, what is actually happening is that the maximum of one wave is falling on the minimum of the other, and what you obtain is the difference of the amplitudes, and in such a case the interference is said to be destructive. And thus interference patterns are made up of points of high and low intensities which correspond to constructive and destructive interference respectively. So how do we decide if a point on the interference pattern is going to be a point of high intensity or a point of low intensity? Or in other words, how do I know whether constructive or destructive interference is going to take place at a point? Just to recap, constructive interference takes place when the waves from the coherent sources exactly line up or match up with each other. That is, the crest falls on the crest and the trough falls on the trough. On the other hand, destructive interference takes place when the crest of one wave falls on the trough of the other. So we want to find out if we can predict what will happen at a particular point, and we'll do this mathematically. We know that for interference we have to take two coherent sources and apply the superposition principle to them. So let's say that I have two sources, y1 and y2. Their equations are written as follows. Y1 is equal to a sine omega t and y2 is equal to b sine omega t plus phi, where a and b are the amplitudes of these waves and phi of course is the constant phase angle by which the second wave leads the first wave. The fact that I have used a constant phase angle while describing it mathematically shows you that I am using coherent sources. We know that coherent sources have constant phase relations, and thus here we have used two coherent sources. And the next part is predictable. We have to apply the superposition theorem, which says that if I want to find the resultant amplitude of these two waves, I simply have to add up their displacements. That is, the resultant amplitude y will be an addition of y1 plus y2, that is a sine omega t plus b sine omega t plus phi. And now what we have to do is simply simplify this expression. That is, I open up the sine a plus b bracket and then take sine omega t common, and this gives me this huge expression. Now where do we go from here and how do we simplify this further? To simplify this further, we use a mathematical technique. What we do is assume that a plus b cos phi is equal to r cos theta. Let me take a moment here and tell you what we are doing. We are replacing a plus b cos phi with r cos theta. But what is r and what is theta? We'll have to find that out. Basically, we are changing the equation from a, b and phi to an equation which includes r and theta. And why are we doing this? We'll see in just a moment. So just like we substituted a plus b cos phi to be equal to r cos theta, b sin phi is substituted to be r sin theta. And because of this, when I replace these substitutions in that big expression, what I see that it simplifies. I take r common and then I get the sin a cos b plus cos a sin b form in the bracket, which simply simplifies to sin a plus b. And now you see this really nice expression came out where y is equal to capital R sin omega t plus theta. So to be able to write this really simple expression, we had to do those substitutions. And what is the advantage of getting this expression? You see, this expression looks very similar in form to the expressions 1 and 2. So what I have done is try to write the final expression or the resultant amplitude in the same form as that of the individual amplitudes. You have y on one side, you have the amplitude r on the other side, sine, and you have an argument of the sine. So here obviously then r is the resultant amplitude that we want. But what is r even? R is the resultant amplitude of the two waves when they interfere with each other. And basically what I've got in this equation is telling me that the resultant wave is also a harmonic function. That is, it is also a sine function with the amplitude r. And now I want to find r, that is, I want to find the new variable r in terms of the old variables a, b and phi. And to do that, I'll simply square and add equations 3 and 4. And when I do that, I'll see that they simplify and I'll get that r is equal to root a square plus b square plus 2ab cos phi. That is, the resultant amplitude of these two waves is given by this expression and denoted by capital R. Once we have the resultant amplitude, we can take a look at some specific cases. It is obvious that since A and B are constants because they are already predetermined that the waves have an amplitude A and B, the only thing that is changing is phi. And therefore I say that when cos phi is 1 in this expression, you will see that it clearly turns out that R turns out to be equal to A plus B. And this is the sum of the amplitudes of the two waves, which is nothing but the maximum value of the resultant wave. We also know that intensity is proportional to the square of the amplitude. And therefore, if I want to find the maximum intensity, it will be proportional to the square of the maximum amplitude. Therefore, I say I max is proportional to R max square. And we just saw that R max is A plus B, and therefore I get I max is proportional to A plus B the whole square. And if I remove the proportionality sign, I get that I max is equal to K into A plus B the whole square. Now similarly, I can do that for the minimum case, that is when cos phi is equal to minus 1, which is the minimum value of the cos function. I'll see that the expression for the amplitude, the resultant amplitude R, becomes R is equal to A minus B. And this is nothing but the difference of the amplitude of the two waves, which gives me the minimum value of the resultant wave. And thus the minimum value of the resultant wave takes place when cos phi is minus 1, and this value is given by A minus B. Similarly, now I can say that the minimum intensity will be proportional to the square of the minimum amplitude of the wave, and therefore I min will be proportional to R min square, and so I get that I min is proportional to A minus B the whole square. Removing the proportionality sign, I get I min is equal to K into A minus B the whole square. From this, I can get the ratio of the maximum and minimum intensities, that is I max upon I min will be A plus B the whole square upon A minus B the whole square. Finally, I can also note that if B and A are equal, that means the two waves who are interfering, if these two waves have the same exact amplitude, then the maximum amplitude of the resultant wave will be 2A and the minimum amplitude of the resultant wave will be exactly equal to 0. And why is this important? It is important because the minimum is 0. That means the region of low intensity will be perfectly dark, and the maximum is 2A, which is the maximum value that you can obtain when the waves are interfering. Therefore, if you have interference between two waves which have the exact amplitude, the contrast between the bright and the dark interference fringes will be the best. So here we undertook a quantitative explanation of the interference of light. From this, we can find the average intensity, that is I max plus I min upon 2. And if I take the equations from equation 2 and 4, I will see that I average turns out to be simply K into A square plus B square. It is important to note that this average intensity does not change whether interference is taking place or interference is not taking place, and this proves to us that interference is nothing but a redistribution of energy. We can also write down an expression for the resultant intensity. In fact, we have already written this before, but here we can use and continue this analysis. That is, we know intensity is proportional to the square of the amplitude of the wave, which means that I1 will be equal to Ka square, I2 will be equal to Kb square, that is the individual intensities before interference, and the resultant intensity IR will be equal to Kr square, where R is the resultant amplitude after interference. From here, I can say that IR is equal to K, A square plus B square plus 2AB cos phi, because we know R is equal to root A square plus B square plus 2AB cos phi, and this gives me that IR is equal to Ka square, which is nothing but I1, plus Kb square, which is nothing but I2, plus this extra term which we long before have called I12, which is the interference term, which in value is equal to 2 root I1 I2 cos phi. And we have seen this expression before, but here now we derived it from first principles. So IR, which is the resultant intensity, has this expression, that is I1 plus I2 plus 2 root I1 I2 cos phi is the resultant intensity when two coherent sources interfere. From this, I can get the conditions of constructive and destructive interference. That is, for constructive interference, now it is obvious that constructive interference takes place, which means IR will have a maximum value, and that will be maximum when cos phi is maximum. So constructive interference takes place when cos phi has the maximum value, which is plus 1. And this corresponds to the angles of 0, 2 pi or 4 pi. And in general, then I can say that the phase difference should be 2n pi to give us a constructive interference. From here again, path difference, which is given by lambda upon 2 pi into phase difference, will come out to be n lambda simply. So this is the condition for constructive interference, that the phase difference between the two sources should be equal to 2n pi, where n can be plus 1, 2, 3, etc. And the path difference should be n lambda, where n again can be 0, 1, 2, 3, etc. So here you see this is the condition for constructive interference. Similarly, then I can find the condition for destructive interference, that is cos phi should be equal to minus 1, which is the minimum value of the cos angle, which will give me that the angle phi is equal to 0, 3 pi, 5 pi, etc. And therefore, the phase difference for destructive interference comes out to be that the angle should be an odd multiple of pi, that is 2n minus 1 into pi. And from here again I can find the path difference x, which is lambda upon 2 pi into phi, which will give me that the path difference should be equal to 2n minus 1 into lambda by 2, and therefore these two are the conditions for destructive interference. So this was a quantitative explanation and discussion on the conditions for constructive and destructive interference. But I want to take this time out to discuss how and what does constructive and destructive interference mean qualitatively. If you want constructive interference at a particular point, all you really want is that the waves from the two sources should reach the point in such a way that the same shape of the wave reaches it. As you can see from the picture, when these two waves starting from S1 and S2 are reaching point P, the crests of both the waves are reaching point P simultaneously. So at point P, both of them have the shape of a crest, and therefore constructive interference takes place when the shape of the wave reaching the point is exactly the same. And from here, if I want to ask what is exactly the path difference between them, and I take them apart and I see that the path difference is simply lambda. Similarly, I can see that the next situation in which there will be constructive interference at point P will be when again there will be a path difference of 2 lambda. So you see the path difference of lambda, 2 lambda, 3 lambda each time means that the same shape is reaching point P, and so in general I will get that for constructive interference the path difference should be n lambda, and then I'll apply the formula that phase difference is given by 2 pi by lambda into path difference and get the answer for the phase difference as well. Similarly, if we do a qualitative discussion of the condition for destructive interference, we'll see that destructive interference will take place at a point if the waves reaching at that point are opposite in shape. Or you can see in this case the wave from S1 has a crest and the wave from S2 has a trough. So when the crest of one and the trough of the other reach the point at the same time, in such a case you have destructive interference. And very clearly, if I take them and align them and I check what is the path difference, I'll see that in the first case the path difference is lambda by 2, in the second case the path difference is 3 lambda by 2, and then I see that in general if I want destructive interference, it means that the path difference should be an odd multiple of lambda by 2, and so I get my general formula that path difference is equal to 2n minus 1 lambda by 2, and then to find phase difference I simply multiply that by 2 pi by lambda, and I get that phase difference should be 2n minus 1 pi or odd multiple of pi in order to get destructive interference. So you see we got the same conditions for constructive and destructive interference even by just simply qualitatively analyzing what exactly should happen, and it was much easier to come to this conclusion. The phenomenon of interference was successfully demonstrated by Thomas Young in a very simple experiment in 1802. We have already seen that interference can only take place when you have coherent sources, which means that if you have two sodium lamps illuminating two pinholes, we will not observe any interference pattern because we said that you can't have coherent sources if the sources are independent. So to overcome this drawback, Thomas Young devised a very simple plan. What he did was illuminated two pinholes S1 and S2 by a single pinhole, which was in turn illuminated by a bright source. So he created two sources from one single source. So here you can see that we have a bright source which is illuminating the pinhole S, which in turn illuminates the two pinholes S1 and S2. The light waves spread out from S and fall on both S1 and S2, and S1 and S2 then behave like two coherent sources. Thus, when a screen is placed at a large distance from the pinholes S1 and S2, alternate bright and dark fringes appear on the screen. This is the interference pattern. These fringes disappear if any one of the sources S1 or S2 are covered. The appearance of bright and dark fringes on the screen can be explained on the basis of Huygens principle. According to Huygens principle, the source S sends out spherical wavefronts. These wavefronts reach the pinholes S1 and S2 simultaneously, which in turn become secondary sources of light. Thus, S1 and S2 are coherent sources. The solid lines represent the crest of the wave, and the dashed lines represent the troughs. The bright fringes on the screen correspond to the positions of constructive interference when the crest of one wave falls on the crest of the other, or the trough of one wave falls on the trough of the other. The resultant amplitude and hence intensity of light in this case is maximum. Similarly, the dark fringes on the interference pattern correspond to the case where the crest of one wave falls on the trough of the other, or the trough of one wave falls on the crest of the other. The resultant amplitude and intensity of light is hence minimum. These bright and dark fringes are alternately placed in the case of an interference pattern. In addition, they are also equally spaced. These are also known as interference fringes. The exact positions of the points of maximum and minimum intensity can be calculated for the Young's double slit experiment, similar to the analysis undertaken for the interference of light. In this case, we draw a diagram joining S1 and S2 and the point S with the center of the interference pattern. Here capital D represents the distance of the pinholes from the screen, and small d is the distance between S1 and S2. Thus, the position of maximum and minimum intensities can be calculated for an arbitrary point P. In order for the point P to correspond to a bright fringe, that is to a point of maximum intensity, S2P minus S1P, which is the path difference between the waves which are starting from S1 and S2, should be equal to an integral multiple of lambda. This is the condition for constructive interference as we have learnt before. That is, the path difference should be equal to n lambda. However, from the figure, it is clear that S2P square is given by d square plus x plus d by 2 the whole square, and S1P square is equal to d square plus x minus d by 2 the whole square. Thus, S2P square minus S1P square can be simplified to obtain a value of 2xd. Rewriting S2P square minus S1P square in the form of a plus b and a minus b, we get that S2P minus S1P is equal to 2xd upon S2P plus S1P. Now, we assume that x, which is the position of the point P from the center of the interference pattern, small d, which is the distance between the pinholes, these two values are much smaller than the distance of the screen from the pinholes. Thus, we are considering a case when the screen is at a large distance from the source. In such a case, S2P and S1P can both be approximated to be equal to capital D, and S2P plus S1P can be replaced by 2D. The 2's cancel, and S2P minus S1P approximately comes out to be xd by d. This is the condition for constructive interference in the Young's double slit experiment. From equation 1, then, we can say that n lambda is equal to xd by d. From here, I obtain the position of the bright interference fringe that is x is equal to n lambda capital D upon small d. This is the position of a bright interference fringe. Similar analysis can be undertaken for a point of low intensity or a dark fringe, and we obtain that a dark region at a point is obtained for the position x such that it is an odd multiple of lambda capital D upon small d. Thus, dark and bright bands appear on the screen, and these are known as the interference fringes, and their positions are given by the above formulae. The fringe width, which is nothing but the distance between two consecutive bright or dark fringes, is given by subtracting two consecutive orders of the fringe. From here we obtain that beta, which is the fringe width, is equal to x position of the n plus 1 fringe minus the x of the nth fringe, which gives me that beta is equal to lambda capital D upon small d. It is also clear that because the central point O lies at equal distance from points S1 and S2, the point O will be maximum because the path difference is 0, and this corresponds to a case of constructive interference where the value of n is 0. In order that the fringes obtained are nearly straight lines, the distance of the screen from the sources must be much greater than the distance between the slits. Thus, for capital D much greater than small d, the fringes are nearly straight lines. From the formula of the fringe width, that is beta is equal to lambda capital D upon small d, it is clear that fringe width depends upon the wavelength of light. Beta is directly proportional to lambda and hence increases for the red wavelength and decreases for the violet wavelength. Similarly, it is clear that beta is inversely proportional to the distance between the slits. And finally, it is directly proportional to the distance of the sources from the screen. It must also be remembered that the angular separation of a fringe does not change with increase in the distance of the screen from the sources. Even when the screen is moved, the angular separation of the fringes does not change. Finally, note that if the location of the source S is shifted by an angle, then the central fringe on the interference pattern also shifts by the same angle but in the other direction. This means that S dash, R and O dash are always on a straight line. If a transparent sheet of refractive index mu and thickness T is introduced in one of the paths of the interfering waves, the optical path length of this path increases by mu minus 1 into T, and therefore, if the present position of a particular fringe is given by y is equal to capital D upon small d into delta x, where delta x is the path difference, then the new position of the fringe will be given by replacing delta x with delta x plus mu minus 1t. So it is clear that mu minus 1t is the additional path difference introduced by this transparent sheet that we have placed after S1. Thus, the shift in the fringe will be given by y dash minus y, that is given by subtracting 1 from 2, and we get that the lateral shift of the fringe is given by y naught is equal to capital D upon small d into mu minus 1 into t. However, we know that the fringe width beta is equal to lambda capital D upon d, and therefore capital D upon small d can also be written as beta by lambda. Replacing this value for capital D upon d in the lateral shift expression, we get that y naught is equal to b by lambda into mu minus 1 into t. This is the expression for the lateral shift of the fringe. As this expression is independent of n, therefore, each fringe or the entire pattern is displaced by the same amount. The shifting takes place towards the side in which the sheet is introduced, and the fringe width does not change. So this completes our discussion on the concept of wave optics and the interference of light. I hope you enjoyed the video. Thank you for watching. So thank you for watching this video. If you like our channel, please subscribe to it by clicking on the link here. And if you'd like to buy your very own target book, you can click on the link here. Thank you for watching and stay tuned for more updates.